things I have to deal with is taking things personally. Seriously, it's like, in the end, nothing's personal. I just need to tell myself that over and over again. We can talk about this. This is great. This is great. I made some comments. And
Okay.
literally one of the few things I did after returning last night.
Okay.
Woo. Okay. Yes, abstract algebra. Okay, since it's been a while, let's just take a minute to bring this home. I need it just to settle in. So just a couple of minutes of letting go. So sitting up straight, eyes closed. Noticing the sensation of your feet. Can you feel the bottom of your foot? Can you feel your big toe on either foot? Can you feel both big toes at the same time? Here's a challenge. Can you feel that second toe next to the big toe? And move your way across and see which toes you can notice the sensation of. Can you do them at the same time? Which ones are stronger? Give those toes a wiggle. Let's come on back and do some abstract algebra. Awesome. All right, so I've got some things to talk. I mean, we're not going to do new stuff today because what I would love is, so the due date was Wednesday, right, for the current homework. I want to see how much of that we can get addressed today and like kind of get back onto a good schedule so I can give you a new one on Wednesday. Oh, joy. So, my friends, I know Sydney has some questions on the homework. Why don't we just start there? And then I'll add things in as we go along.
I have WTF right next to number 13.
Awesome. Awesome. Oops. Okay, cool. So, let's get some stuff up on the board. So number 13, these markers are not bad. See, they've gotten rid of all the WD-40, probably for better. So show that this, let's call it S, set under multiplication modulo 4, so with times mod 4. That's a little dicey notation there. You don't know if it's a time sign intended to be. Is not a group. So Sydney, how did you? Was this the one you had a challenge about, or was this the WTF?
I think it was the other set.
Okay. So for this one, if anybody hasn't, I would just recommend making a multiplication table and making sure that you're closed under multiplication, right? That's like a kind of a first order thing. Am I closed? And then take it from there. Do I have an identity? So forth. So you were actually asking about, it's not a group, but that 1, 2, 3, 4 mod 5 multiplication is. So this, so here, just make a Cayley table. that should answer your questions about that. And then the next one is 4 times mod 5. Is that right? Okay. Cool. So like what was the TF part here?
So when Olympia and I were doing it, I got stuck on the inverse part, because like with the first one, I understand that 2 doesn't give you an inverse, obviously, because you can't do 2 times any number to get your identity.
I'm not sure I agree.
You serious? Okay, so
I'm
maybe
totally
I don't
serious,
understand.
dude. I am totally serious. So did you make a Kaylee table?
I did not.
That's going to be my recommendation. Like when you have this group and it's so small, right? It's compact. I can deal with this like physically by writing, emotionally, because it's not going to take too long. But yeah, here I would put times mod 5, and and I don't want to do this because I do want you to do it, but I think that would be the step that's going to let you know. First off, am I closed? Right, I have to answer that question. So nothing besides 1, 2, 3, 4 can show up in here. Do I have an identity? Does every row and column have exactly 1, 1?
Oh, okay.
Well, right. Well, and I should back off. What is the identity for this group? It's going to be 1, but I want to say that, right? So the identity. Let's just be clear about that. It's 1. Because we're just doing normal multiplication, so nothing freaky. And then, do I have inverses? So the inverses is there exactly 1 identity? And I'll say it kind of, because it might not always be 1, but identity element in each row and column. And if so, then everybody has an inverse. So if 2, for some reason, 2 times 3 was 1, then I know that 2 inverse is 3. And so that's, yeah, does that make sense?
Yeah.
And I can list those all out. And then, let's see, then what else do I need for a group? Associativity. So let's talk about how to cheese this.
What did you just say?
Cheese this.
Okay.
You never heard that phrase?
No.
We talk about, like, in video games, we like cheese bosses and stuff like that all the time. You like exploit the system to make it work against itself and help you. So, associativity, cheese. Yum. Okay, so associativity. We're using standard multiplication. It's mod 5, but at its heart, it's still multiplication underneath. And I can fall back on you can say multiplication is an associative operation, right? And then modding things doesn't change its behavior. So for associativity, you're like almost never going to, especially when it's true. So when you suspect it's associative, and it will be with all these mod groups, addition and multiplication. So let's just talk about that, since multiplication is associative, so is mod n. So we've got that. But when you suspect it's not associative, so you're like checking through this stuff and maybe the table looks weird. You'll get used to looking at these tables and detecting if they're a little odd. Or you just know it's the problem saying, show this isn't associative or something like that. Then you have to come up with a specific example. Like a quick one was last time is Z with subtraction associative. And we did that, I think we did that last. Yeah. So there I had to come up with a specific example. And so 2 minus 3 minus 4 is, and I work that out and show that's not equal to 2 minus 3 minus 4. Just kidding. So I think this will help you. Yeah? Does that sound good?
Yeah.
What else we got? said there was multiple
Yeah.
triple letters.
Number 5, C.
Okay.
I guess B2, but.
Oh yeah, this is great. I want to talk a little bit about UN as well. I think. So let's see here. Find the inverse of the element under the operation. Oh, okay. So C and B, because I didn't assign D, so everybody just B. I didn't want to. It's like I just didn't feel like talking about complex numbers. Like you know about them. You haven't had complex analysis here yet, probably, right? Yeah. So it was just like, let's just avoid that. We're going to talk about matrices, that'll be enough. So what I would first do is take a look at this group UN. Do you understand what UN is, or do we need to talk about that?
I think I got that part.
You got that? Okay, so that's going to be, let's just make sure, or we'll just write it up here for posterity's sake. So UN is going to be all integers between 1 and n minus 1 that, and that's inclusive, that are relatively prime to n. And let's talk about why. This is something we never got to address, but like, why is this group defined this way? And we need a result first, and the result is this one here. So let's add some deeper understanding of UN. So we can show, here's kind of a claim, that the equation AX mod n equals 1. So this is normal times in here, so this is times standard multiplication, has a solution, a unique solution, n 1 to n minus 1, if and only if A is relatively prime to n. Okay, already hating this marker. Fade on me. Oh, yes. Okay. So let's just take a look at it, because this is basically saying in mod n multiplication, A has an inverse whenever A is relatively prime to n. So what does it mean to be relatively prime? So let's get a definition. We would say A is relatively prime. I'm kind of set my abbreviations are becoming sparser and sparser. Relatively prime to n, if and only if. Can you help me out here? What?
Greatest common divisor is 1.
Beauty. If GCD of A and n equals 1. Cool. And we're going to kind of do one of those if and only if proofs all the way through, so you can read it down, and then if you want the other direction, you read it backwards. Have you ever seen that? So you've got a proof and you want to show blah, if and only if blah. So you start with blah, and then you get if and only if blah 1, and blah 1, if and only if blah 2. And you work this little chain down, and then I have blah n, if and only if triangle. And then, so this flow goes this way, but then because of the if and only ifs, it's also a proof in the other direction. So it's a nice, fast way to do things. So, cool. When I think about GCDs, what's a great equation or equivalent statement that I could go to? And it's one that you and I talked about a little bit. Oh yeah, shoot, what was that? And I know we've all talked about it together. What's another characterization of GCD of A and N is 1? Let's play hangman. Okay. There you go. Okay. Yeah, the linear combination thing. So that's a really important result. Like you might, when you're doing some of these problems, want to have like a little note sheet of just some of the really important results. This is one of those results that you're going to come back to over and over again throughout the entire course. So that is true if and only if there are unique S and T integers such that A times S plus T times N times T equals 1. Such a weird result. So strange, and not at all the way we've ever thought about GCDs, but in this class it's going to be the way we think about them quite often. Okay, so let's see, where do we want to go? Ooh, let me be more suggestive. Sorry here, not like, you know, racy suggestive. I'm gonna like pull my shirt off my shoulder or anything like that, but because I don't want to get fired. And you don't want to see my shoulder. Lots of reasons. So I'll be a little bit more suggestive because I'm looking at that AX mod N thing. So now check this out. So this is true if and only if AX equals 1 minus NT. How do I get to the thing that I want to show, the AX mod N equals 1 from there? Why does that follow immediately? What does mod mean? What does it mean to be equal in mod? Maybe we should write that up. And there's like a secret mod N over here, right? There's like a hidden mod N. So we would say that blah mod N equals blip mod N if and only if what? Here, oh, okay. They differ by what? This is good. I'm glad we're back together. What do you think, Kyle?
N.
Yeah, N would work. Would 2N work?
Yeah.
Any multiple of N.
Yeah.
Yeah, exactly. So if they equal to some multiple of N. Yeah? Yeah.
I haven't had any food this morning.
It's okay, man. And it's just like first time back together again. Everything's, and me being sick is all a big clusterfuck.
Yeah,
So,
right.
and now it's not ready for children. I have to mark not suitable for children. So, why is this that? This is very good. Let me write this statement. Let me write this. So this means, let's be a little more precise, and maybe this will help. This means blah minus blah equals some multiple of n, where t is an integer, right? And that means this equals this plus a multiple of n.
Yeah.
Do we see that happening
Yeah.
here? Yeah, like literally AX and 1 only differ by an integer multiple of n. That minus is tricky, just from the way, yeah, but it's still just a multiple of n. So, this is true. Let's see, note that AX and 1 differ by, and I would write this down because it doesn't seem, I'm not getting the sense that you're like, dude, why are you wasting my time with this? Differ by an integer multiple of n. So that means that this is true if and only if AX mod n is equal to 1 mod n. Buy that, Kyle. Check it out. It's okay. Just take your time. Let's make sure you're on board. showed you this. If I said that 7 is equal to 3 mod 4, mod 4, let's put 7. Now let me do a better one here. What about this? Does that seem right to you? Yeah, because 9 is equal to 1 plus 4 times some multiple, right? Like
Yeah.
so? Yeah? Does that help a little bit? Okay, cool. Good, good. So you want some protein bars or something?
Oh, I'm okay.
You're okay?
I'll go crush a breakfast after class.
Okay. Are you sure?
Yeah, I'm alright.
Okay, I got food if you need it, man. Okay. So anyway, there's this result right here. This equation has a unique solution if and only if A is relatively prime. So that means that if I take this group, so let's take a look at a specific one like U12. It's going to be 1.
No,
What's the next entry?
5,
5,
7,
7,
11.
11. Yeah. And that's it, right? Because 11 is the most we would go up to anyway in this group. So each one of these has an inverse only because they're relatively prime to 12. Let's take a look at like this equation right here. Take one of the ones that wasn't. 3x mod 12 equals 1. Does that have a solution? So let's think about what that means. It means that 3x equals 1 plus some multiple of 12. Can you think of an integer multiple of 12 that, hold on. I got a better way to see this, sorry. Let's take a look at a different way. Let's look at a little multiplication table here. So here's times mod 12. And let's put 3 here, and then all the various, like why didn't we put 3 in there? And let's see. So 3 times 1, mod 12 is 3, 6. We haven't broken over the barrier of 12 yet, so we don't have to really do any modding. 9. Notice that none of those are in our group so far. They're all sour in this group. So what's the next one? 0. Definitely not in our group, right? But what we're hoping for is a 1 in here. If I find a 1 in this column, that means that times whatever that thing was equals 1. 3 times whatever equals 1. Let's keep going. 15. 3. Next.
6.
Yeah. It's real pretty, isn't it? 0. 3.
6.
Love it.
9.
Boom. There's no inverse in the multiplication sense. There's this real foul 0 thing that gets in there, and that's not even considered as part of our set, so it's not even really closed under that. If I include the things that aren't relatively prime to 12 in there. So good Lord, that's just more talk about these U groups that I definitely wanted us to do, but I don't think I answered your question yet, Sydney. So help me remember what question it was.
We're finding the inverse of 13 in U14.
Thank you so much. Okay, cool. So what is 13 inverse in U14? So what I would do here is first write out what U14 is. Let's go through that. So tell me what's in here.
1, 3, 5, 9, 11, 13.
Beauty. Cool. So we're thinking about 13. So I'm going to put 13 here, and then I'm going to put the elements of the group. And for right now, I'm going to brute force my way through this, right? So we got 13 times 1 is 13. What's this? And remember, we're doing mod 14. What's the next one? Kind of tricky, actually. What's 39 mod 14? Yeah, that sounds right. What is 85 mod 14? Who the fuck knows? I don't. Let's look at the multiples. Sometimes when I'm doing this mod stuff, I like to have the multiples in front of me. So 28, 30, 42. Thank you. 42, 56, yes, 70, beauty, 84, and we can stop there. But you see, like, by having those multiples, it makes taking the mod a lot easier. Just find the one that's closest underneath and take the difference. So here we got 85 mod 13 is 1. And there's the inverse of 13.
Oh.
Yeah, does that make sense? You see, yeah, let's stop and make sure that is making sense. Yes. Yeah. Yeah. Trinity, is this like working for you? Okay. Okay. And that'll be unique. That has to be unique in a group. We know that these U groups are we're kind of demonstrating it in part in this problem. So let's take a look. I'm sorry, what?
Okay, what was it? That was 5B.
Yeah.
Cause, okay, so the answer to 5B is 13.
4 times 13 is 65. So yeah, this 169, 13 times 13. Well, wait, did we find these mods wrong over here? 14. Let's see. Okay, let's double check my work over here. So 14, definitely a multiple of 14. Pretty good on that one too. We had 14.
Those are all fine.
Yeah.
It's 5 times 13 is
65.
65.
Okay.
yeah.
Okay.
It's good to have a sober person driving. All right, so exactly. This is 65. Thank you. So what do we get? 9. And then keep on going. So 13. Let's go down to 13. 13 squared is 169, and we still have to like build up our table a little bit. Or let's just do 169 divided by 14 at this point. So it goes in 1, I got 29, goes in 2, and I have a remainder of 1. So that remainder is the mod part, right? So that would be 1. So there we go.
Okay.
So now the answer makes sense. Thank
Yeah.
you, Trinity. Helping me multiply. Okay. So let's take a look at that more nebulous question. Basically, they're hypothesizing. Let's see. So when we were in U12, what was the inverse of 11? So let's just take a look at that real quick. So when we had 11, and this is times 12, and we got 1, 5, 7, 11. Let's get some multiples of 11 out. So 11, 20. Yeah, those are super easy. Yeah, I'm very happy, right? Let's just have them on the board for sanity's sake. And then what's the next one? 110. And then 121. Beauty. So we got 11. 55 goes to. Wait a minute. Oh, this is mod 12. Son of a gun. Yeah, good lord. So sorry. Mod 12. Me. Are you already seeing it, Kyle?
Yeah.
Okay, what do you think? So
7.
77 mod 12.
72.
Yeah, it's 5. Yep, 77 goes to, yep. And then we got 121. 12 is, well.
Yeah, because 12 times 10 is 120.
Exactly, yeah. So notice that again, that the very highest, the last entry in the group turned out to be its own inverse. In that one, it was its own inverse. So we get this maybe our hypothesis is n minus 1 will be the inverse. So what is n minus 1? And maybe we can even do a proof. Let's just see. I'm not quite sure, but I'm curious what that would look like. So again, this is mod n, right? So if we take n minus 1 times x, and this is going to be mod n equals 1. Let's just look at that equation. Solve for x. In un. So let's write out what that means. That means that n minus 1 times x equals 1 plus some multiple of n. That's a good way to do it. Maybe let's go the other way. Let's just do our hypothesis. This is painful. Sometimes you try something and it doesn't work, so you try another approach. What about just n minus 1 times n minus 1 mod n? What is that going to equal? Because then that would show it's its own inverse if we get 1 out. So how do we do this? Let's FOIL, right? So n squared minus 2n plus 1. Why is this equal to 1? Do you see it? So this is equal to 1 plus, I'm going to rewrite it, n squared minus 2n mod n. Why do I get 1 from that? These are both multiples of that, and so they don't change the, God, I thought that was Diana. I would have been so excited. Yeah, so Diana, I would have been excited if I'd seen you. So this is equal to 1 mod n because n squared minus 2n is a multiple of n. So in some ways, I think I pretty much just answered the question, actually. Just have to write it up pretty, put some words in, and understand it, of course. That's the key thing here. You good on that, Kyle?
Yeah.
Okay, awesome. What else, my friends? Anybody else? Let's just check on anybody else's questions. Nothing specific.
For what I did, I was okay.
Okay, cool.
Just generally, I wanted to know how to prove that, like, those are groups, but we kind of did that with 13.
Yeah, so so do you want me to talk about it again, or you're uncertain?
I think I'm good.
Okay.
Like, if you just set up your Kaylee table and go through the 4 and make sure you can.
Totally, yeah. Closure, identity, inverses, associativity, which will be like.
Yeah.
Yeah, what do you mean? Kind of, yes.
Perfect.
Yeah. And that, like I said, Kaylee table, beautiful approach when you have a finite group. Sydney, was there anything else, my friend?
Can you read number 20 again?
Yeah, let's take a look.
Because I didn't do it, which means there was some no more notice that went on in my brain.
Fair enough.
Yeah.
Yeah, do we see how, yeah, let's take a look at that together. Do we see how to approach that problem? I mean, step 1 is getting a D4 Kaylee table out. You can find a D4 Kaylee table, I think in the book, we have one. If not, you could easily look, yeah, we do. So on page 29, there is a D4 Kaylee table. So let's look at what we're actually trying to do here. So there's 2 things. First off, what is the square? What is the collection of all squares of elements from D4? How do I find that from this table? What does that correspond to in the Kaylee table on page 29? what sub-collection of D4 corresponds to the square of every single element in D4? So let me write the setup here, because I saw a pair of eyebrows kind of go up there, maybe. Maybe I'm wrong.
No, you're not wrong.
Okay, so I thought. I'm a face watcher. There's a lot of mathematicians who can't read faces. I am not among them. So the set of all x, let's call it S, such that x is an element of D4. So that's the first set we want to find. The square of every single element. How do I find that from the Cayley table? Yes, the diagonal. So whatever's on that diagonal is perfect squares. Does that make sense, Sydney?
I think so.
Okay, awesome. So then the other one is, we'll call it T, is the set of all x in D4. It's kind of the inverse question. Not really. Such that x squared is the identity element. What is the identity element in D4? R0. So let's be more precise. So,
68.
say that again.
So 68. I think that works for me.
I'm sorry, I can't understand what you're saying, Kyle, sorry.
So like, the square of that,
Yeah.
R0, but, and it's the same thing for 180 in each of these, but the square of R90 and 270 are both 180.
Oh.
So those were-
Gotcha. Yes, yeah, so it's the collection of things, it's really just a sub-collection of this set.
No.
It's the subset of the diagonal elements on that table that actually are not. So certain things are gonna be in there, like are not, that's a pretty easy one. And then R180, and you can decide if there's more or not. But you shouldn't have to look real hard.
HVD, T inverse.
Yes. Make sense? Yeah. Groovy. Yeah, it was. There was D, right? Some of the flips. Aren't the flips giving us R naught?
Yeah.
Yeah.
Of the flips.
Each of the
Squared
flips,
is
absolutely. Yep.
Cause you flip it and then flip it back.
Yeah, makes perfect sense. Yeah, exactly. Each of the elements that are their own inverse. That's another way to think of this. Who's their own inverse in D4? Cool. So that problem's not too bad, right? Sydney, or
Not anymore.
not anymore. Beautiful. Let's see if we can make other things better. Thank you. You have a book though, right?
Yeah.
Okay, cool.
I just don't carry it
Awesome.
around.
Awesome. Probably for this class, not the worst idea, or maybe.
Yeah,
like a-
I'm learning that. I should probably bring it to this.
Yeah, it definitely, we will probably refer to it quite often. Sometimes I'll just like, nobody's gonna wanna watch me write the theorem on the board. Okay, so what other problems were in that set? So let's see, 30 or 15, what was 15 like? How about 15? Can we take a look at that together?
Okay.
Okay, I'm gonna run to the restroom.
Okay.
Did you get 15 already?
Yeah.
Oh, you knocked it out. Which ones have you not done yet? 30? Are you good on 30?
I don't know if I'm good on 30.
But you have an answer.
I think.
You got some? Okay, we'll talk about it.
Okay.
Let me run to the restroom real quick. So you don't really have anything to do though. Should I give you something? Do you want something? Why not I just go to the damn bathroom and come back?
What are your guys' opinions on a group chat?
Maybe that for.
Could be helpful. Could be helpful. Sick. Get in there, Trinity. done well.
I kicked a concrete stair this morning walking up it, so it's nice and bloody.
Oh.
Yeah, he's like focusing the toes. I'm like, my toe really hurts.
Oh no!
Focus on
Sorry.
your toe.
No, it's all right. Yeah, I kicked a concrete stair on the way to practice this morning.
Ouch.
So just a big chunk of skin came right off.
Oh, good lord.
That's disgusting.
Sorry.
Yeah.
I'll, no, when we do this in the future, I'll add alternatives. Unless your toe is missing.
AKA Kyle.
Yes. Probably most likely of us to hurt yourself physically, I think. I don't know. Yeah.
Soccer does. It's just a constant state of sore.
Yeah, your thigh is shredded. Dude.
Oh yeah, it looks.
That's
great.
another one.
It looks better than it did yesterday, actually, considerably better.
Is that from soccer?
Yeah, it's just
Kyle's
when you
mess.
slide, it just tears the skin off.
Kyle's a mess, dude. Ew.
Yeah, got ankle tendonitis, all sorts of stuff's wrong. It's just kind of go. You just
Just work through it.
So maybe we shouldn't
Yeah.
focus on any part of the body.
Yeah, right? I know, right.
Upper body's fine.
Okay.
It's-
Fingers.
Good to know. Okay, fingers. We'll
Fingers.
stick to fingers.
Cool.
Yeah, you shouldn't be using your fingers too much, right?
No, I'm not
Some
going
kind
to
of
the
penalty.
Yeah.
Okay, good. Okay, good. I know very little about sports, but I know that. So wait, where were we doing? Sorry, we were looking at,
So you wanted to talk about 15.
yes. Does everybody feel confident on how to do 15? That's what I mostly want to ask.
I agree with you, but
Sure. Yeah, so right, sorry Val, yeah,
Yeah, I
of
guess.
course, yeah. Trinity, you're feeling like, or do you need a little tip, or are you good on that one? Good on that one. Okay. Kyle, do you feel okay about that one?
that's one of the days.
Well, look, I can give you a little tip if you want.
Sure.
But, so like if I knew, and I won't give the exact tip, but if you had a group element and I knew that a to the 27th power was e, then I also know lots of things because of associativity. I can rewrite this as, oh, a to the 13 times a to the 14 equals e. So the inverse of a13, a to the 13th is a to the 14th. That's the game. Cool, awesome. Just wanted to make sure everybody was rolling up. Thank you, sir. And so then, the last one was number 30, and with that one, we have this collection of group elements. What is the collection, or what is the inverse of a product? So let's just take a look at a simple, if I have A, B, C in a group, and I want to find its inverse element, how do I solve that?
This is just 1 over.
Ooh, this is good. I'm glad we're having this conversation. So, say what you're gonna say a little more.
Well, I guess you don't. I don't know. It looks like it would be 1 over.
So I'm glad you said that. So let's never divide in here.
I'm sorry. What?
No. So this in a group that is a multiplicative group, like the real numbers, and if I said to you, what is 3 inverse? Then that's the solution to this in multiplication terms, right? So real numbers. So then here x would be 1/3 if we're in the reals, let's say maybe the positive reals or something like that under multiplication, standard multiplication. But this is only in a multiplicative group where things work out well, because we saw a little bit earlier, for example, in a multiplicative group, 13 inverse was equal to 13 in that U14 over there, right? And so this doesn't, we don't really use that notation. It's the same idea, but we don't have division per se, really. So, and one of the hard parts of this class is to like pull away from like those old habits. And so that's
Sick.
yeah. So, Let's go a little slower here. Oh, what's that? I'm sorry, go ahead, Pat.
Isn't technically x just equal to ABC though?
Yeah, so let's,
Because of,
and actually what I meant was this, sorry, let's take that off, because I want the thing times ABC, right? So let's reassociate here. So first off, X needs to undo this C, right? So when I write out X, it needs to have C inverse on its left, right? So putting something here, I would need C inverse, and then that undoes this. So once those two collapse, then I'm left with AB times something equals E. What needs to interact with the B? B inverse, then A inverse. So let's check that out. If I said, what is ABC times C inverse B inverse A inverse, then reassociate. So this is A, B, C, C inverse, B inverse A. So that now I'm using the associative property, and now those become E. And E times anything is just that thing. So this is, if I was going super slow, I would write it out like this. So then that's equal to A, B, B inverse A. See how it's collapsing like a little accordion, just from the inside to the out. Oh, that should be A inverse there. So this is like sometimes called the sock shoes property. Did you read that in the book? And you have to think about it in a very different way. We don't know that this is multiplication. So we don't necessarily have multiplication going on here. It's some weird operation. And the way I think of this is, first I did C, then I applied B, then I applied A. So when I put on my shoes, when I get dressed in the morning, I put on my socks, then I put on my shoes, in that order. How do I take them off? Well, the first thing I take off are my shoes, so the inverse is shoes off, then socks off. Does that make sense? Yeah? So very, very different ways of thinking. And this class is all about destroying anything you thought you knew. So,
that's good.
yeah, it is good. It is good most of the time. It's always good to tear down pre-existing assumptions about the world. Cool. So I think we should be good to like rock that, right? So we can collect this Wednesday, start a class. Does that sound good?
Cool.
Awesome. Solid. I want to do a few more problems together in class. So Kyle, I'll let you use my book here.
I'll start bringing it.
Thank you, Sam. I kind of wanted to work on number 7 together because I was looking at it this morning, and I was thinking, I don't know. So, and we're gonna be using those modular matrices probably numerous times for examples and counterexamples. So let's talk about it at least today. So first up, let's talk about the part A there. What number did I just say we were doing?
7.
7. Chapter 2. 7. And we have A. So we have this group. It's GL Z4. Is that right? How they're?
Yes.
Yeah. Okay. And that is the collection of 2x2 matrices where A, B, C, and D are elements of Z4, so they're going to be these things right here, yeah. And every operation, addition and multiplication is going to be done mod 4. And then we also have this condition that says AD minus BC is not equal to 0. Do you remember in linear, everybody's had linear algebra, right? So this is the determinant. And it's just saying that this thing can have an inverse, potentially. So again, that's the determinant. And this is all, again, everything mod 4. So I think, what are they asking us? Would you just read it to me, Kyle, please?
Yes, says which of the following sets are groups under matrix multiplication?
Awesome, thank you. Under matrix multiplication. So, group. Let's play the game. What do I first need to check? Closure. All right. So let's review matrix multiplication just for quick. I'm sure we all can do it, but you know, what the hell? Because it seems to be the heart of all of this. So A2, B2, C2, D2. How do we multiply matrices?
Cross
Yeah, row, column. Yep. So take the dot product of the row with the column. So we've got A1, A2 plus B1, C2, and then C1, C2, row, C1, A2 plus D1, C2, let's see, so now my second, oh yeah, so now I just use the second column. It's been a while since I've actually multiplied matrices. Same, cool, that's good, I'm glad we're having this chat then, that's very good. So C1, A2 plus D1, D2. So that's how we're gonna multiply, and then all this stuff is gonna be done mod 4, and we're gonna simplify it out. So would there be any reason, let's talk about it. Would there be any reason that these operations, mod 4, would produce something not mod 4? And why? So why are all these elements in in this set Z4? So all elements in Z4, because what? I mean, we could check it, but boy, I don't want to make a Cayley table for this. No.
Did I multiply? I got something different in the bottom.
Oh, let's see, maybe I screwed up.
I got C1, B2.
B2, thank you, Kyle. Yes, absolutely, you are correct, sir. Thank you. Why are all those? And let's, it's like kind of like a sentence. Because a more hangman, hang person is yeah. Nice. Under what operations does it need to be? Addition and multiplication. Yeah?
Yeah.
It's closed under mult and addition. Yeah, so that knocks out closure. And having that structure there makes it very evident to whoever's looking at this. It's just times and plus, so that's all good with that group. So we got that. So closure. Check. What next do I need? Identity. What do you think the identity element would be here?
1001.
Say, yeah, the classic, right? Yeah. Awesome. So it's still just matrix multiplication, right? It's just matrix multiplication, mod 4, and so nothing unexpected would be happening. This would still give you back whatever you multiplied it by, either side. So it's a two-sided identity, just what we need. So that's our E for the group. What else do I need to check? Inverse and associativity. So let's go for the low-hanging fruit. Why do I have associativity? Or however you spell it. That's not it. But think again, like sweeping sentence. What things do you know are associative already? Addition, multiplication. And here we're worried about associativity of elements, right? So we're worried that I've got some matrix times some other matrix times some other matrix equals, because these are the elements of this group, right? They are these matrices. Why can I do that? So it's not quite that. That's true, Kyle, that the addition and subtraction, and this is kind of part of that, but what, at a higher level up than just like the actual computations, what matrix multiplication, beautiful. So you always fall back on, you know, just the basic things you know. Matrix multiplication is totally associative. So here, we're just doing it, and then we're mod 4ing it, and modding things doesn't screw up properties for the most part, except maybe this next one, and that's why I saved it for the end. So now we gotta check for inverses. And with that mod 4, that's a little scary to me. That scares me. Just a little bit. And it might be okay. But this was what I was wrestling. I didn't have time to fully wrestle with this before class, but maybe we can wrestle with it together. Maybe there's a nice simple way to see it. So does everything in that group have an inverse? Can we construct something? Can we find some matrix in there who has no inverse? So what worries me, just a little bit, is that this is 4 here. That this is 4, not like a prime number or relatively prime to everything underneath. So like in here I've got this 2, and I know that 2 squared is 4, which is 0, right? So in this group, 2 squared is 0. That scares me a little bit. So, where do we go with this? Like, how do we convince ourselves it's either true or false? Can we find an element without going through, God, how many elements would there be here? So let's see, we have 16 elements in this group, because there's 4 possibilities for each entry. There's less than that, because not all of them. Like this, is this in the group? Is that in the group? What are things in the group? So this is, that's in the group. That's cool. Because AD minus BC is equal to 1. Yay, it's not 0, but what about AD minus BC here? It's 0, yeah, so it gives us 4. It's 4. No, you totally know how to multiply, you got it. So yes, 4 mod 4 equals 0 mod 4. So that would not be in there. So that's the kind of stuff that's like making me nervous about this group, or its grouphood. I wonder how we could show that everybody had an inverse without doing this freaking Cayley table. We could try some things. Yeah, and then we won't just like sit here for 15 minutes in silence staring at this, or maybe we should, I'm not sure. That's, I mean, it's math class, right? It's 15 minutes is not long in a math world. Well, so I think it probably is, and here's what so GL stands for General Linear Group. So it's making me think this thing probably is okay, and probably that condition that AD minus BC is not zero is saving our butts, because then I wouldn't have things like that. But I was kind of hoping one of you would have a fresh perspective on this. That I'm just missing. Like, why is this true? It would be cool if it was just like a simple thing, like one of these sentences. So yeah, this morning I just spent time trying to come up with elements of that group when I multiplied them together. Or somebody without an inverse. But we already have closure. Oh, whoa. Okay, hold on, me.
Okay.
Why is closure, why did that not demonstrate closure? So that, I think I made a boo-boo. Why is that not a demonstration of closure? What was I forgetting? What property of being in this collection did I not address? Look at that. So I just said, they're all in Z4, so we're done. What did I not address? What's a critical element in that definition of that set right there? Keep moving to the right.
Is the resulting determinant is zero?
Yeah, exactly. So I didn't address the determinant part of this at all, being non-zero. And that, now when I look at it, I'm like, oh my God, that's a lot of algebra. I mean, this is abstract algebra, but that looks unpleasant. So let's just say, unsure, I'm gonna back off that original claim, because maybe that's where this thing fails, because that question's even a lot deeper than that. Can we find a couple of elements in here? And let's just start playing. Let's be mathematicians and start experimenting. So let's find somebody who is in here. So for example, 0, 1, 2. And I feel like it's gonna be, I feel like the 2's are gonna play a role somehow, because if we can get up to mod 4, yeah, if we can produce somebody whose determinant is 0 when I multiply it by something else, so something here, is there any way to do this so that I get a determinant 0 thing? So I think this one's okay. That has a determinant of -2 in mod 4, that's +2. So this thing has determinant 2. Oh, sorry. Okay, I'm like just going up here, but like, hopefully this is okay. This is like kind of thinking and like trying to share my thought process. I also know this. How does the determinant of a matrix relate to the determinant of its inverse? Let's start pulling out some things we know. Yeah, or the inverse, right? So yeah, it's the multiplicative inverse. Okay, so the determinant of A inverse is equal to the multiplicative of that. Yeah. So what is the multiplicative? See, because in that group, 2 doesn't have a multiplicative inverse. So let's look at this. So if I have the integers mod, so this is C4, it's 2 times 2 is 0. So 2 doesn't have an inverse. That was the thing that was really getting me unnerved about all of this. 2 times 2, so 2 inverse does not exist in this group. That thing has determinant 2. So I'm starting to maybe have convinced myself that this is not a group. I can't find, because 2, there is no one of these. Well, determinant equals 2. Determinant of the inverse must equal 2 inverse, and that does not exist. Ooh, okay. So this thing should not have an inverse. Is this any of this making sense? Because I feel like I might just be talking to myself. I'm not sure. I'm definitely doing some of that. But so here's my reasoning. Let's just go through it to see where I'm coming at. So first off, this was an illuminating idea that the determinant of the inverse is the inverse of the determinant. And that should still hold true here. So I found something that had determinant 2. And I could have come up with a simpler one. I was making an even simpler one. That's so much nicer, right? Yeah. That should not have an inverse because there is no multiplicative inverse for 2 in this group. So let's see what happens if I do this and then I multiply it out. So that's going to be A, B, 2C, 2D. And if I want that to equal, if that's supposed to equal the identity, what would that say? Well, that would say that A had to be 1. B would have to be 0. 2C mod 4 would have to equal 0. And 2D mod, I think we might be fine, D. I think we might be onto it. 2D mod 4 would have to equal 1 of mod 4. So, what is twice all these numbers? So here's the numbers that we have. So our original set is 0, 1, 2, 3. So this is D. Here's the possibilities for D. And then here's 2D. And that's going to be 0, 2, 0. What's 2 times 3? 6, but mod 4, 2. Can I solve that equation in mod 4? No. So this matrix can't have an inverse in there.
Nice.
Holy smokes. Yeah, relieve our, is this making some sense? Like, if not, I would love to help clear it up. Because I think it was an important discussion. Or whatever, that wasn't quite a discussion. So let me just reiterate, let me sum up what I just did. I'm thinking that this thing has got several issues because in mod 4 multiplication, 2 doesn't have an inverse. And this is all about multiplication, so I'm thinking, okay, if simple 2 does it, then I start putting it into these fancier constructions, seems like that would get blown up if I did things just the wrong way. So I created a matrix from this collection, GLZ4. Its determinant is 2, so it's in that group, all good. And then I thought, what is its inverse? And its inverse would have to be some matrix in GLZ4 that times this one gave me the identity. So I'm basically trying to construct an inverse for this matrix. When I did that, I did this multiplication here. So that times that arbitrary matrix is this matrix. And then that would require that A is equal to 1, B is equal to 0, 2C is equal to 0, mod 4. So like here, C could either be 0 or 2. Either one of those would work. So that's not a problem because both those are in there. But then when I got to this, 2 times D would have to be 1. And that has no solution in the group because 2D is never equal to 1 in this group. So I can't find anything. I can find other stuff. I got this, I can do this, I can do this, I'll put a freaking 2 there, but there's nothing I can put here that will give me a 1 out over there. So yeah, kind of? Yeah. Now I'm not saying you know, you might do this the same way, but hopefully there was some benefit in like thinking it through together here in this room. And let's just call it. So yeah, so please get those homeworks in good shape for Wednesday. New stuff will come in. If you want to, you could start reading chapter 3. Not the worst plan on finite groups. Thanks, friends. It's good to be back. Oh, thank you, sir. Yeah, I would have told you could have walked out.
I don't need to.
No, you don't. And you're not a